Hello everyone, welcome to Kirchhoff's law. Let us see if we can understand this law in a very simple way. To understand to this further, let us just briefly recall the symbols we are going to use in this topic. Cell will be shown, as you can see, with the long and a short line. The longer one is positive, the shorter one is negative. Battery, which is a combination of two or more cell, will be shown like this. As you can see, for the two cell, and if it is more than two cell, then you show with the dotted lines. So more than two cell switch, which we will not be using much, but however, in case we have to, we will be using this way. Bulb, we are going to use the X symbol within a circle. Resistor, we are going to use this symbol. So let's begin. Now here we have a very simple circuit, which I have just designed using our FET simulation. And if you see the circuit one, which is a very simple circuit, and that shows, right now what you're seeing is the direction of the charges. Okay, the black color is the negative end. So it is showing the flow of the electron, not the current. Remember, the current always flows opposite direction to the charge. So in the simple diagram, we can see the electrons are carrying energy, the bulb is glowing. Now coming to the second circuit, where we have two cells here. And these two cells, if I click here, each one of them is 9 volt. That and this, both are 9 volts, so which means they are same potential difference. And as you can see, the electrons are flowing on one side with the current of 0.39 ampere, on the other side with 0.42 ampere, almost that close enough, and then they get added up. So when I show the current direction, I'm going to show the other way around, okay? Because current direction is always shown from positive to negative. And then we have the third diagram here, which shows what happens, if you change the polarity of one of the cell. So as you can see, this particular cell, I have rated it as 12 volt. I have taken a 12 volt, whereas the other one is just 3 volt. So there is a difference of 9 volt. So definitely it means that my first cell here, the 12 volt is supplying greater amount of energy to the electrons. So the electrons which are moving from the 12 volt cell are pushing all other electrons even through the cell 2, which is a 3 volt cell. So just remember this, because when we do the circuit and the Kirchhoff problem, we will be using this idea there. Okay. Right. Now this is how we saw. So don't consider the video, because that was showing the direction of the flow of charges. And as I said that, current flows opposite direction. The direction of current is always from higher potential to lower potential. So if this is my positive and this is my negative, then the current direction has to go from here. And if you remember, this was 9 volt. This is 9 volts. This is also 9 volt. And again, this is positive. This is negative. So current direction goes this way. They both come here. And then this point that you see here, where both the charges, they come and meet, is called your junction, is the junction. And then both these charges move together up here. Okay, so it is something like as if I have current I1, I have current I2, and then I have current I, which is nothing but I1 plus I2, because after all, current is nothing but the amount of charge flowing per unit time. So if the total charge, which are coming from, this side and this side, they combine, then they go up together. So if this is, for example, 0.4 ampere, and if this is 0.4 ampere here, then this current here will be 0.8 ampere, right? They get added up. So that was about when you have 9 volt and they are placed the way you see them. What happens, if I change the polarity here? So I change the polarity of one of the cell and I make it 12 volt, whereas the other one is 3 volt. Now, in that case, there is a difference of the energy. So, right, we all know that from positive, the charges have to start this way. Whereas the charges here, when they start, they will go up here. So, which means technically they will come like this. Now, the problem is that because this is our first cell, let us say, okay, and this is the second cell. This is the second cell. So, because the first cell has a greater potential difference, it has a greater amount of energy, because 12 volt basically means 12 joule per second. Something like, if you recall the V factor, which is a W by Q, it's amount of work done per unit charge, which is nothing but 12 joule per coulomb. So this much energy is being supplied to every coulomb of charge. Okay. Now, because here the 12 volt is greater than the 3 volt, so instead of the current flowing here this way, what happens is the electrons here are all pushed this side. Okay, all pushed this side, this is pushed this side, because the potential difference of first cell is greater than the second one. And then ultimately the current direction changes here like this. Okay, so in this case, what happens if this is I, it gets divided as your I1 and I2, and this is your, again, as we called it, your junction. Okay, this is your junction, right? That was a basic fundamental about how the current actually flows when the potential difference is same and the cells are arranged in one particular way, and when the potential difference is, different. So I hope this part is clear. Now let us go ahead and see how the law actually is applied. Now, first law, Kirchhoff first law, is something that we just now saw, right? So at a junction, okay, a junction in an electric circuit, remember, junction has to be shown with a symbol of, I should have added in the first place, but it's okay. So it will be shown like this. That's a junction. Okay. Now, at a junction, the sum of all current is 0. Okay. What does it mean now? It simply means that if I have current I, which was coming here and now got divided into two parts, which it has to go in a two different path, which is I1 plus I2. So therefore, your current I is nothing but I1 plus I2, right? That is a basic logical understanding. This is a logic understanding. And what I can do is I can shift both of them this side. In that case, they are going to become something like this. Minus I1 minus I2 equal to 0. But I can also modify this plus, and I can put the minus I1 inside bracket. I can put again plus, because mathematically it won't make any difference, right? We all know that. So technically, if you see here, it is nothing but sum of all current, okay? And that's equal to 0. But we have to also keep in mind that the sign convention has to be applied. So the sign convention has to be applied. Okay, has to be applied, right? So that is Kirchhoff's first law, which is very simple to understand because it's also a logical one. Let's look at the second law now. Coming to Kirchhoff's second law, Kirchhoff's second law says that, sum of all the EMF in a closed loop, in a circuit is 0. Okay, so there are two things that, sum of what? Sum of EMF where in the closed loop. Okay, that is 0. How? Let us understand. So if I have a cell, for example, okay, I'm going to show a cell, and then I'm going to add, a resistor here, external resistor R. Okay, now I very well know that this is positive, this is negative. So my direction of current has to be this way, right? I. And then it goes through this, like this. Now, if I supply an EMF of E, then the potential difference, if I measure across R, let's say I measure it using a voltmeter here, then this V will read here as your IR, correct? From Ohm's law. We get this from Ohm's law. Okay. Now, in that case, if there is no loss, in case there is no loss of energy in the circuit, which is ideally not possible, there will be some loss, but in case there is no loss and the resistance of the conductor is minimum, then in that case my EMF itself will be nothing but IR, isn't it? So therefore I can also write this as, I can shift the IR this side, which will become minus IR equal to 0. So it is nothing but, I can again use the mathematics little bit here to support me, right? This is nothing but, you see, it's like as if minus V equal to 0. So sum of Again, you see the plus symbol. So it means sum of all EMF, the voltage, technically. Okay, voltage. Now, this is very interesting actually. If I have, for example, if I have, a complex circuit, then also this rule will be very easily applied. It is applicable in any complex circuit. All right, that's a good advantage of Kirchhoff law actually. So we are going to apply this law, but when we apply the law, we have to use certain rules because the sign convention here is very important, right? So the sign convention is very important. Okay, very important. If you look at this equation, when I wrote this equation E plus of minus IR, so you see this is negative, right? This is the negative sign, whereas my EMF is actually positive side. It has a positive side. Now, in order to make things simpler, what Kirchhoff suggested is when you take a circuit, you decide a sort of direction that you want to choose. Okay, in the closed loop. So for example, let us say this was a circuit. Okay, I'm just drawing again because I don't want to spoil the first circuit. Now I have to choose a direction here. I'm taking clockwise direction. Okay, I'm taking clockwise direction. So I have taken clockwise direction. Okay, clockwise direction. Now I will try to understand how that formula can be applied. Now look at my direction. In my direction, I am going this way, okay, for the cell. So I am moving, it's like as if I am moving from positive terminal to negative terminal. In that case, my EMF is positive. So therefore, case 1, if I keep, if my direction is from positive to negative terminal of cell, I will take plus E. Okay, I'm going to take it as plus EMF. All right. And if it is vice versa, then I will do the other one. Okay, so it is vice versa also. Then second one is case 2. In case 2, what am I doing is that if my direction is opposite to current, then in that case, I will choose. Now look at the current here. Now my direction here is going this way. See, at the bottom. So, and current direction is going this way, right? The current is going this way and my direction is this way. They are opposite to current. Then I will take V as negative, and that's why we are getting here minus IR. Okay. So we are going to follow this rule when we solve the question. With this rule, it becomes very simple to solve the Kirchhoff law questions. Right. Let us now start, solving first case. So let me take one example here. Let me take, this is positive, negative. Okay. And then I have a resistor here, which is R. I'm going to take a simple circuit here now. Okay. And then let us take another one. So I am having here another R, which is R1, R2. Okay. Like this. Now, let us say this R1, first one is 2 ohms, R2 is, let's say 6 ohms. Okay. And let's say we are supplying an EMF of 12 volt. We are asked to find the direction of current here. So we need to find direction of current. Direction of current. How do we find the direction of current? Now, this is positive and this is the negative of the cell, which means technically the current will flow this way, current will flow this way, current will go down here, which means my current, which is coming here, I, will now get divided as I1 and I2. So across the resistor R2, I will have current I1. Across resistor R1, I'm going to have current I2. You can take any way you like. That's not a problem, right? So potential difference across R1, that will be your let's say V1, which is your I2 R1. Okay, I2 R1. And potential difference across R2, let us say that is V2, it will be I1 R2. Okay. Now I'm going to choose. Now there are loops here. There are actually technically, if you look, there are 3 loops. One loop is this one, right? One loop is this one, and one loop is also the full thing if I ignore the center one. But let us make it simple. I will take this as my loop 1, okay? And I will take this as my loop 2. And as usual, I will take our clockwise direction, okay? I will choose the clockwise direction like this. Now, first, let us work in loop 1, okay? In loop 1, okay? So we are going to work in loop 1. Look at my direction now. I am going upward. I am going upward, right? Which means I am technically going from negative to positive. Remember what was the condition we took there? We said that if you go from positive to negative, only then it is plus E. If you go vice versa, the sign will change. So technically it means here, because I am going from negative to positive of the cell, so it becomes minus 12, right? See? Now, what is the next potential difference we have to see? Next is across R1. Look at the R1. I am coming down. Okay, I am coming down like this in my direction. Look at the current direction now. Current is going same as me only. Both of us are in the same direction, right? Me and the current I2. So in that case, what happens? So if you are opposite, then we take negative. But now they are not opposite, right? They're in the same direction. So which means I have to do it plus. And then I have to do it as your I2 R1, I2 R1. And then that total should be 0 in loop 1. All right. So technically, this means plus 12 plus I2, which I don't know at the moment, R1, which is 2 ohms. So into 2 is equal to 0 in loop 1. Now let us work in loop 2. So in loop 2, what happens? Let us see. In loop 2, if you look here, there is no cell here. So we have to just judge from our direction. Now in loop 2, it is other way around, right? Here I am coming down. See, my direction is downward. Whereas the current, if you see, current is also downward. Okay, so both are in the same direction. So what do you think I should take here? Both are same direction. So definitely I have to take plus, and then that will be my I1 R2, correct? Now let us look at the other resistance. So in my direction is going upward here. See, my direction is going upward, whereas the current is coming down here, I2. So they are opposite. Opposite means you remember it is negative. And then I have to do here I2 R1. And that has to be 0. So if I have to write this, I will just write it I1 times R2, the value of which is 6, minus I2 times R1, which is your 2, equal to 0. Or in other words, I can write 6I1 is equal to 2I2. I can just cut this 3 times. And I can write I2 is 3I1. Yeah. And this is from the second loop we got. In the first loop, if I continue solving, what will I get? I would get 2I2 equal to 12, right? If I shift the negative 12 this side, which means I2 will be equal to 6 ampere. That I can now put here. So 6 ampere is equal to 3I1. So which means my I1 is going to be 2 ampere. So I have I1, I have I2, and my I will now be 8 ampere. Okay. So this is how we actually solve these questions. All right. There are many ways one can actually test. So if you want to just check, we can check this because it's a very simple circuit. Okay. So if I use the total resistance formula, remember the parallel formula is 1 by 2 plus 1 by 6. So 1 by R is 6. So it is 3 plus 1. Then it is 1 by R, which is 4 by 6. So it is 2 by 3, which is 2 by 3, which means my resistance is 3 by 2 technically. So total resistance. In that case, I can find the total current, which is my total voltage by total resistance, which is nothing but 12 by 3 into 2. So it is 3 4 ja, 4 2 ja 8. So I get 8 ampere. So this method is okay. If it is a simple circuit, this is simple circuit and your resistors are parallel. So it is okay. We can cross check, but in a complex circuit, it is very difficult. We cannot cross check. Okay. So that is how we actually work. So which means technically that our values are correct. So the answer should be absolutely correct. Let's go for a little complex circuit now. Okay, so rough work. We don't need this because we have already done it there. So if I have to solve with 2 cell, let us take now 2 cell. Okay, so I'm going to take 1 cell here like this. Okay, and then I'm just checking how I have done there. So I'm going to take now R1. Okay, I'm going to take one more here, R2. Then I'm going to add one more here, cell. Okay, like this. Let's say this is 6 volt. Let's say this is 9 volt. Of course, this is positive, this is negative, this is positive, this is negative. So the direction of current will be here like this, from positive through this, this becomes our junction. I hope I marked the junction in the previous circuit. It was not marked. It is very important that you show the junctions very clearly. That's a very important thing. So here also we have 2 junctions. Okay, now both of them will combine and then they come this side. So technically I can again show, maybe the first one I can show this time here I1, maybe I can show this as I2 and this as I. So it definitely means that my I is nothing but I1 plus I2, because both of them are actually combining to form I. So this I can take it as equation number 1, right? Now what I have to do, I have to again choose 2 loops. So I have chosen again, let's say first loop and second loop. Again, I'm going to take my clockwise direction here. Okay, and I'm going to work again same way, the way I did it in the other one. So for R2, can I now write here directly? So I can just say that, okay, this is my V2, which is I2 R2, and this is my V1, which is I R1. Okay, so let us now work. Start in loop 1. Let's say in loop 1, what happens? In loop 1, through the cell, I am going up, right? I am actually going upward. Now I am again going from negative to positive. So what happens to the EMF 6 volt? I have to take him negative 6, because the rule we set there was positive to negative is plus 6. So sign convention minus. Now look at the other side. I am moving down. Okay, I am moving down. So current is also same. Current is also moving down. So both are in the same direction, which means I have to do plus. And then all I have to do is IR1. Okay, and that should be equal to 0. So which means minus 6 plus I, which I don't know, R1, which let us take a value, something like say 3 ohm. And let us take R2 as 5 ohms. Okay, so which means into 3, that should be 0. So I will take this as, okay, I can still solve this question. So all I have to do is 3I is equal to 6. So my I is 2 here, ampere. Okay, so I just got my I. Now let us see in loop 2 what happens. In loop 2. Now in loop 2, again, my direction is downward. See, this time it is downward, and I'm moving from positive to negative. So I can take plus 9, right? Now let us work on R1 now, V1. Now I'm going up here, this side, and the current this side, I is coming down. They're opposite to each other. So I have to do it minus V1, right? Minus V1. Now look at the R2. I am going this way. Okay, I am going this way. Current is going other side. So we are opposite to each other. So minus V2. And then that is 0. So if I have to just substitute the value V1, it will be nothing but IR1, and then V2, which is nothing but I2R2 equal to 0. So which means 9 minus I, R1 value is 3 minus I2 into R2, which value is 5, that is equal to 0. So it is 9 minus 3I minus 5I2 equal to 0. I is already known to me, 2. So I can put here minus 3 into 2 minus 5I2 equal to 0. So which means 9 minus 6 minus 5I2 equal to 0. I can shift this side. So it will become 3 equal to 5I2. So I2 is technically 3 by 5, which is your 0.6 ampere. Okay. So therefore, if I2 is 0.6 ampere, then what is my I1? From equation 1 we can do. So from equation 1, we can find that I1 is nothing but 2 minus 0.6, which is 1.4 ampere, right? And that makes sense also. Why? Because less current, I2 is less because there are 2 resistors there. Okay, so that's affecting that actually. Okay, so this is how you solve Kirchhoff questions. And always the loop. Remember, the loop is the game here. Okay, main point here. So that's all. And this PPT was completely prepared using the Microsoft PowerPoint template and digitally written by Wacom Intos. Okay, and the simulation was from FET, as I've already mentioned. This is just to resource because I have used their resources in order to design this. Thank you very much.